Hello, good evening. Today is February 23rd and it's around 7:40 p.m. Dallas, USA time. That is the Central Standard Time. And I'm making this placeholder recorded presentation. And this is a placeholder just in case there's an internet glitch, because at around 10 o'clock, 10 p.m. Dallas, USA time, which is around 9:30 Indian Standard Time. That's in the morning, 9:30 a.m. on February 24th. I will be giving this keynote address live. And so I always make a presentation, a recorded presentation, a placeholder presentation, just in case there is an internet glitch, technology glitch while I'm giving the live presentation. And so I'm Bhavani. I am a professor at the University of Texas at Dallas, Founders Chair Professor of Computer Science, and I'm very honored to give this presentation. So what I'm going to do now is share my screen. Okay. Okay, so as I said, this presentation will be given February 24th, 2022 at 9:30 a.m. Indian Standard Time, which is going to be February 23rd, Dallas, USA time, around 10 p.m. USA time, February 23rd. Now, the conference will be starting at 9 a.m. Indian Standard Time, which is 9:30 p.m. February 23rd, USA, Dallas time, that is US Central Standard Time. Okay, so my keynote address, integrating data science, machine learning, and cybersecurity with applications in Internet of Transportation and infrastructures. And so when I say data science, machine learning, it is essentially artificial intelligence. Okay, so I've got three parts to my presentation. Part one, integrating cybersecurity and AI machine learning data science. Okay, and I call it SecAI. And so under that, I will talk about big data security and privacy, privacy-aware quantified self, data science machine learning for cybersecurity applications, securing data science machine learning AI techniques. And then I'll talk about trustworthy machine learning AI. And also part two will be security and privacy for the Internet of Things, and in particular, Internet of Transportation and infrastructures. And part three, I will talk about applications of security and AI for Internet of Transportation and infrastructures, essentially applying part one to part two, and that's going to be part three. And so I would like to thank a number of our sponsors, the National Science Foundation, Army, Air Force, NASA, NIST, NSA, and several of my colleagues, Professors Alvaro Cardenas, Murad Kantajalu, Latifa Khan. So Alvaro Cardenas for the work on Internet of Transportation, Murad Kantajalu about secure data science, ML/AI techniques, and Latifa Khan for data science machine learning for cybersecurity applications, and our former PhD student, Dr. Raul Quenenes for security and privacy for Internet of Things, and our project coordinator, Ms. Rhonda Walls. Okay, so part one, integrating cybersecurity and artificial intelligence for machine learning data science. Okay, so motivation, data science, security, and privacy, or data mining. It used to be called data mining, by the way. From data management, we went to data mining, we went to data science, and now it's all about data science, machine learning, and AI. Although AI and machine learning were around for a very long time, but over the last 10 years, it has really, gone really big. It's really booming. Okay. So why is it booming? Because of the deep learning, because now, especially also we have data, we have lots and lots of data that we can apply all these machine learning techniques, we can train them, and then we can test. And so partly because of the advances in data science and also advances in machine learning. So integrating the two, we've got, and deep learning, we've got lot of progress has been made. Okay, so I believe I introduced the idea of data mining, security, and privacy. So what are some of the privacy concerns that can result due to data mining and how data mining can be applied to solve security problems. And this was at a keynote address, first at the IFIP 11.3 in 1996 in Italy, and then later at the Pacific Asia Knowledge Discovery Conference in 1998, and then subsequently published a landmark paper. I call it landmark paper, I'll tell you what, because I was at NSF, a program director, and when you're at NSF, of course, you give out grants and so on. So when you publish a paper, a lot of people quote that paper. So that was in 2002, and that spawned a new area of research. So at the same time, around the time, IBM Almaden Research Center, where Dr. Rakesh Agrawal and his team, they came up with privacy-preserving data mining. So they said, you can have data mining, but at the same time, you can ensure privacy to some extent. So you have the original data, you add noise added is X prime, you modify data mining process, but the final result has to be the same. So essentially what you are doing is adding sort of a privacy metric. And this privacy metric could be perturbation, could be randomization. So some of these techniques, ideas are now being applied for fairness, right? Because you are adding a fairness metric, right? So that's what a lot of people are working on today. These data science AI techniques have to be fair and not biased. So our research with a PhD student, myself and Dr. Murat Kantajulu, we advised a PhD student, Dr. Li Liu. She focused on privacy-preserving decision trees. So since these people worked on privacy-preserving association rule mining, there was a lot of work on privacy-preserving neural networks, privacy-preserving decision trees, privacy-preserving practically for every machine learning technique. And she also focused quite a bit on the perturbation method. And so that was sort of especially a perturbation method was significantly improved from prior methods. And then now we have this big data problem, right? Massive amounts of data being collected and analyzed. So data mining, security, and privacy is exacerbated with big data and data science. And so I hosted an NSF workshop on big data and security and privacy in September 2014 and presented the results to the Interagency Working Group in Washington, DC in February 2015. Okay, so what is this big data management, security, and privacy, right? There's a lot of technological advances, novel applications. So it is now possible to capture, process, analyze large amounts of data for security tasks, as well as for other tasks. You talk about financial applications, healthcare applications, medical applications, retail, manufacturing. So you name it, practically every area is being enhanced, right, with machine learning, data science, even food science, right? Food, nutrition, what's the best foods for us, for our health. So they analyze our health, the way we are, and so on, gather data about us, and then they can give us some good advice as to what are the best foods to take. However, such tasks, such as user identification, access control, anomaly detection for security, right? You can apply data science for authentication, access control, anomaly detection, insider threat detection, and so on. But you can analyze integrated data collected from the web. You can identify connections and relationships among individuals. And this in turn can help with homeland protection, disease outbreaks, and having better lives. But the problem is this collected data, even if anonymized, so you've got multiple records about yourself, but they're all anonymized, but you can put all these records together and infer something about the individual, right? You can re-identify the individual. So that's the challenge, right? So if you can say, if there's my address, you remove my name, and my healthcare records, you remove my name, and say these healthcare records are associated with this address, you can easily go and look at the directory or whatever and identify me, right? So that's the challenge. Security tasks such as authentication and access control, they also require detailed information, right? Because you've got multi-factor authentication. So you've got to collect fingerprints and various other things, right, about a person. So with multi-factor authentication, you can have all these problems, privacy problems. So the information, if misused or stolen, this can lead to privacy breaches. Directions include secure. So what did we discuss at the workshop? How do you secure the data, right? That's access control models. privacy enhanced techniques. So what do we mean by privacy enhanced techniques, right? This, as I said, privacy technique, the data machine learning techniques, they have to be, privacy metric has to be incorporated. Then how do we apply big data analytics, machine learning, data science to cybersecurity? And I'll talk about that, and in particular, I'll talk about insider threat detection. And then how do you secure the machine learning techniques? What do we mean by that? The machine learning techniques themselves could be attacked. So we are applying machine learning for financial applications. And imagine if those machine learning techniques are attacked, and for financial applications, which will say buy, say Microsoft, instead of buying Microsoft, which is really good for today, maybe, it'll say buy IBM, which might not be so good, right? And so you can have chaotic situations. Imagine applying machine learning techniques for healthcare and medicine. If you attack it, instead of saying you've got COVID, it'll say, oh, you've just got a cold. And that could be devastating, right? You can have devastating consequences. Okay, so we came up with this project, Privacy Aware Quantified Self. So mobile devices, so we are carrying these smartphones, and let's see, that reminds me to switch my smartphone off. Smartphones and become a prevalent computing platform for billions of users. We all, almost all of us carrying smartphones, billions of us, right? So there is this recent emergence of quantified self movement. Psychologists and sociologists are studying this problem, gathering data about individuals from the wearable devices and smartphone applications. They have been analyzed to give guidance to the users in improving their health of personal life habits, right? So wouldn't it be great if I open my refrigerator? I love vanilla ice cream and milk chocolates, but I don't keep anything in my refrigerator, because if that's the case, I will be buying vanilla ice cream and milk chocolates every day. So, but let's assume I have that. And when I go to take a milk chocolate, wouldn't it be great if my smartphone gives me a ping and says, look, you're not supposed to eat that, or voice, the refrigerator microprocessor in there says that it's bad for you, right? So it'll be really good, that quantified self. But imagine the problem, because there's so much of data being collected, and this data could be sold to retailers and so on. And so that could be devastating for our privacy, right? So this quantified self, right? You have got cloud-based services to store some of the data that you don't need daily, and some data could be stored on your smartphone, but still all these data collection and sharing it can result in improper uses. And as a result, there could be devastating consequences for your privacy. So what I'm showing here, your Fitbit, and here we are collecting, I think, the blood glucose levels. So for example, data collected by a device monitoring glucose levels might be used for insurance companies. So if insurance company figures out that, say, I've got diabetes, fortunately, I don't have it yet, but hopefully it'll never come. But then not only it's going to damage, right, if I have diabetes, deny coverage, but they might also deny coverage for my son and for my grandchildren. So that will be very bad for them. So such privacy violations could easily get out of control if the data collectors could aggregate financial and health-related data with tweets, Facebook activity, and purchase patterns. This could result in lawsuits against data collectors and psychological and physical distress in individuals, right? So this could be really bad. To address these challenges, we need tools. A quantified self, without a doubt, is good because it will help us for our healthcare applications and so on. And let's say if we are lonely, and then it can maybe connect us with some other people, so we can form a group of those with similar interests. So there are many good things, but so we should have quantified self. But what about how do we bring in privacy? That's our challenge. So what did we do? We said privacy aware, policy-based data management framework is what we have developed. So you have the health information, fitness data, location data, social media data, image, video, all these sources, right? And the data is being collected in your smartphone or Android or iOS, whatever, data collection, data storage, access, data analytics, data sharing. Some of the data in cloud storage and through cloud services, you can get the data. Some could be encrypted and anonymized. So we are saying we need a privacy aware quantified self manager running on our mobile device. But what does that mean? Policies have to guide our data collection, data storage, data analytics, and data sharing. Throughout the entire life cycle, policies have to guide this process. Okay, so what does that mean? Policy-based or policy-aware data collection, storage, access, analytics, learning, and sharing. So lots of data being collected. So storage on the device will not be sufficient. So some of this data will have to be stored in the cloud, whatever. So you have this mobile device, right? Our framework is here. Some local data, but a lot of the data stored in the cloud. It could be encrypted and anonymized, whatever. So based on the access control policies, local apps running on the device will be given some access, right? And some other data based on the policies will be granted access to the cloud-based data store. So, but then we don't want to sort of store everything in the local device. So for instance, we may not need to store the weight of a 20-year-old, right? We may not need to weigh a 20-year-old person every day. Even if you put down, say, 5 pounds overnight by eating a lot at a party or something. But if you're 20 years, it's not going to really, for most 20-year-olds, it doesn't really matter, right? Because it's not going to put a big tax on your burden, on your heart. But instead, if you're 70 years old or even 80 years old, putting on 5 pounds overnight could be devastating. You could get a heart attack because of that. So some people have to be weighed every day, but not everyone. So that's why we can select, right, what data needs to be gathered. So policies will determine that. In other cases, data may have to be deleted to preserve privacy. But then, is the data really being deleted? It's very different when you store your jewelry in a bank. When you remove your jewelry, the jewelry is gone. But in terms of data, if you're storing data in a cloud, and you tell the cloud service provider, I want to remove all my data, it's not like you can take your data and go away. The cloud service provider could make many copies of your data and could sell your data. So you have to audit to make sure that the data is deleted. So there has to be appropriate audit policies. So we envision that data sharing and analytics will be carried out using the services based on different scenarios. Some of the data could be sent without modifications, heart rate, and some you may have to encrypt. But the whole idea is that policies have to tell you what can you collect, right? And how are you going to use it, right? So you can't just say, okay, you can say, I'm going to collect this data, but it's only going to be used for COVID purposes. It's not going to be used for anything else. And you've got to keep your promise, right? There have to be policies. And so policies for data collection, policies for data storage and access, policies for data analytics, policies for data sharing. And when we say policies, I want to just mention one thing is that we have to see, we computer scientists, when we say policies, for us, it's about, policies are like children, right? Children's policies, like I will give you data, like John gives Mary some data or something and tells Mary, okay, don't give this to Paul. I'll only give you provided, it's like I'll give you, I have a secret, but don't tell that secret to Paul, right? So it's like, those are the policies that we came up with. But now we are working with a policy expert. She's the dean of our School of Economics, Policy and Political Sciences. And so she comes up with some very realistic policies for us. Okay, so that's the first part, the big data. I talked about big data. I talked about privacy-aware quantified self. Another area that we are focusing on is data science for cybersecurity applications. And here I'm working with my colleague, Professor Latifa Khan, and it's a big data stream classification. Okay, so what is data science or data mining or machine learning? You use past data to build a classification model, predict the labels of future instances using the model, and helps decision making, right? Now, these 3 bullets, I could have mentioned this 20 years ago. So what has changed? What has changed is this big data stream, massive amounts of data arriving, and you have to develop this model. So let's talk about this, right? Network traffic, financial data, and so on. Sensor data, lots of data arriving, firewall coming into this into the organization, and some attack and some benign. So you can, classification model will decide. The benign traffic goes into the server, attack traffic we block and quarantine. But the thing is, big data, continuous flow of data, massive amounts, and it's very common in our connected digital world. And especially these days, we are even more connected after the COVID pandemic because we are using Zoom and links and WebEx, and imagine so much of data all over, right? Okay, but what's the challenge? The models are changing. The model that was good last week is not good today. This is a problem that we've been trying to solve like 20 years ago, real-time data mining. And we didn't really, the technology wasn't advanced enough to do real-time data mining 25 years ago. But now we have the technology, these techniques to develop models that are changing. So yesterday, it could be by Microsoft, today is by Apple, tomorrow by Google, the next day by what? Facebook, and the next day by IBM and Amazon and whatever. It's changing. So our models have to change. So the model that was valid last week was good last week is no longer good. So models have to be updated. That's our research. So the expert analysis and labeling, there could be a person trying to look at these models, but what we do, person can check from time to time, but we have all these models, right? We have model C1, C2, C3, C4, and all these models work together and decide which ones are good and which ones they have to throw away, that they are no longer valid, right? So that's our work. And we applied this to insider threat detection. What is insider threat detection? Insider threat detection, it requires the identification of rare anomalies in contexts where evolving behaviors tend to mask such anomalies, right? Essentially bad people pretending to be good people in an organization. So that can happen to humans where they carry out espionage, they come in and steal all the secrets and send it to the enemy, they infiltrate into the company and take the secrets. It could be country's top secret information or highly sensitive information, proprietary information of a company when you are developing, say, drug discovery for medications, pharmacology. So that could be a big problem, right? So that's the insider pretending to be a good person. And that's what we are doing here. There are processes that could pretend to be really good. You know, they are application processes and you think they are really good processes, but they can carry out some vicious things. They monitor what's going on, and then they can cause really chaotic situations, right? So that's what we are trying to see, which processes are good and which processes are bad, right? So what we did was, okay, so we have developed ensemble-based. This is ensemble-based classification models and unbounded length, what I mentioned earlier. The result is a classifier that exhibits substantially increased classification accuracy, right? So we use supervised learning, unsupervised learning. For supervised learning, we did traditional support vector machine and one-class support vector machine. One-class support vector machine happens right when you have data that is kind of skewed. That's a good way to use it. And other single model approaches. We also design and develop unsupervised techniques that maintain a compressed dictionary of repetitive sequences found throughout dynamic data streams. And so we also have graph-based techniques for unsupervised. In unsupervised learning, we have to compress because lots and lots of strings are collected sequences. So we've got to compress based on the common behavior. Otherwise, it's too much of data to build a model. And we got some good results in a classifier that exhibited substantial increase in classification accuracy. Okay, sometimes we combine supervised and unsupervised. This ensemble of classifiers allows the unsupervised approach to outperform traditional statistics-based learning approaches, because again, it's not all the time we have the labels, right? We have the labels. If you have all the labels, then it's great. But in many cases, we do not have the labels. Okay, so this is our architecture. Architecture for evolving insider threat detection. So a person is typing away, we've got system calls, we look at data chunks, data is continuously arriving, okay? So we have the ith chunk and we use all that for training, okay? Extract the features, that's really, when you do machine learning, you will learn that extracting the right features, that's really most important. So you extract these features, build an ensemble of models, and then the I+1 chunk arrives, and then you are testing, right? Extracting the features and you test. So that's what we do here. But what are the algorithms? Unsupervised, we use graph-based anomaly detection and also compression-based techniques and supervised support vector machine. And models are updated, ensemble-based stream analytics, and we update the models. Collection of models being developed and they talk to each other or they work with each other, algorithm, and throw away the model that is not producing accurate results. Okay, so that was some very interesting, some of the early work in insider threat detection. Okay, now we go to the other topic. So we finished now. Big data security and privacy, privacy aware quantified self, data science, machine learning for cybersecurity, and now the dreaded problem. What happens if the cybersecurity techniques are attacked? And that's securing data science, adversarial machine learning. And this is with my colleague, Professor Murat Kantajalu. Adversary modifies data to defeat learning algorithms. So we need to understand the adversary. So what the adversary is trying to do is looking at our data, trying to figure out what data we are using to train and thwarting our data, putting some bad stuff. It's also looking at our models, right? How are we developing the models and trying to thwart our models, thwarting our data and our models. So we've got to understand how the adversary is functioning in his or her mind. Then we can thwart the adversary. That's what we have to try and do. It's not concept drift. Remember, I said the concepts are changing, right? Meaning yesterday, Microsoft, today is what? Apple, tomorrow, Facebook, whatever. So it's not concept drift. It's not online learning, right? Adversary adapts to avoid being detected. It could be training time, during testing time. There's a game being played between us and the adversary. So here we are, support vector machine boundary line. The red rectangles are bad instances. The blue circles are good instances. And see what the adversary is trying to do. Push the red, push the red to the good instances. So now we have 1, 2, 3, 4, 5 red instances will not be caught, right? So even if it does that to one bad instance, it can cause a lot of damage for us, right? So we are not catching it, our algorithm. So what do? A support vector machine. Before I give you a solution, we've got to study the attack. There are 2 types of attacks, free range attacks and the targeted attack. Free range attack, adversary can move malicious data anywhere in the domain. So we have, for instance, delta ij, where can we move the data? This is a lower bound and this is the upper bound. This was one of the very first papers, I would say, that was published in this work, in this area. And so our paper, it appeared in the top conference, ACM Knowledge Discovery KDD conference. So the free range attack, where adversary can move the malicious data anywhere. The targeted attack, adversary can move malicious data closer to a target point. So we looked at 2 classes of attacks. In reality, we could have many classes, right? So you can say, what's the point? If you're finding a solution to one problem, but you are not finding solutions to 99 other problems. All the adversary needs is one way to get in. And you are only finding one solution. Adversary has 99 other attacks he or she can make. But again, what we are saying is something is better than nothing, right? That's why nothing is ever secure. So we try to do our best. Okay, so what is our solution, right? So we have these dotted lines, dashed lines are the support vector machine boundary. The red crosses are the bad instances. The green circles are the good instances. Okay, so what we are trying to do, so black dashed line is the standard support vector machine. A threat model, test time, deployment time attacks, attacker modifies X to X prime, modify packet length by adding dummy bytes, add good word to spam email, add noise to an image. Okay. What we are trying to do by learning what the adversary is trying to do, right? Adversary is learning about us and pushing all this red stuff that I showed earlier into the green part or blue part. But anyway, here we have red and green. So we are trying to push the boundary line here, right? Support vector machine boundary line to here, the blue line. So the blue line is the adversarial support vector machine classification boundary. So that means by pushing it, some of the bad instances, red crosses, right? 1, 2, 3, 4, 5, 6, like 8 of them would be caught. Otherwise, they wouldn't be caught, right? Because the adversary is trying to push the red crosses into the green circles. So by moving it here, we are catching some of the bad instances. And so here you can see the black part is like the bad instances. And so by moving it, we are catching many of the bad instances, but still some we are not catching. So you can ask the question, what if we move this right here, the blue line? If we move the blue line right here, right up here, we can catch all the bad instances, but the green circles will also show up as bad instances. So we don't want false positives, right? And that's what will happen here, but we do not want false negatives, which is what would happen here, right? So we want accuracy, false positives, false negatives. That's our challenge. So that gives you a flavor what we are doing. Now, so there's adversarial machine learning, applying game theory, trying to detect these attacks, right? Or trying to handle the attacks to machine learning. But there's also a huge area that's coming along called trustworthy machine learning. And that's now my current area of research. And this really doesn't reflect everything, but I can tell you exactly what's happening. So one aspect of trustworthy machine learning is to do it in sort of hardware. What does that mean? Computations over big data require massive computational resources, and also organizations may use third-party services to outsource resources. So again, we have this big data analytics, machine learning is working on large data sets, massive resources, and often third-party, we give it to third-party to do a lot of the analytics, right? But you cannot trust these third-party, right? So data inherently becomes unavailable in untrusted environments, either observed by man-in-the-middle attacks. So the data that we are sending, outsourcing, could be corrupt, right? So, and you perform big data analytics on the data, right? It's not going to work. If you have bad data, your techniques are not, your model is not going to be sound. So we are conducting research on secure encrypted stream data processing and trustworthy analytics using advancements in embedded hardware technology like Intel Edge SGX to support trusted execution environment. I think I do have a chart. Yeah, I'll talk about it later. But there's also a group of people now focusing on formal methods for machine learning, including logics for specification, for deep learning, and the verification of the machine learning algorithms. So I was on a panel. Actually, the panel was in December 2020, was in India, and I participated. And there was a professor, a lady from University of Oxford in the UK, in England, and she was really doing a lot of research on formal methods for machine learning, right? You make sure that the machine learning algorithms are working according to the specifications. So the Intel platform, as I said, is what we are very briefly, we are trying, it has the application memory, runtime library, and so on, encrypted code. So we're trying to perform the data analytics, the machine learning in SGX enclave memory, in trustworthy execution environments, right? So these are the trustworthy execution environments. And so what we believe is that when this machine learning algorithms are being executed in a trustworthy machine learning environment, they are secure. Okay, so before I go in here, I also wanted to mention one other thing on this chart. So this trustworthy machine learning, at least when I was working on this particular project, I said trustworthy machine learning means machine learning techniques have to be secure, right? That was the definition of trustworthy machine learning. They have to be secure. That means the attacks, they should not be attacked, or if they are attacked, we have to provide these solutions. But recently I finished a paper for an IEEE journal/magazine where I'm providing a broader view of trustworthy machine learning. It's not just me, the community is also focusing on that. It's not just about securing the machine learning techniques. It's also ensuring the machine learning techniques are private, privacy-aware machine learning. It's also ensuring the machine learning techniques are fair and not discriminate. That means they are fair to men as well as women, not discriminate against women, not discriminate against minority communities. And so in terms of giving loans, bank loans or housing loans, sometimes they might, some banks may want to give, because again, it's humans, right? Humans' bias goes into the machine learning algorithms, because if it finds that most of the time, the loans are being given to majority people with the majority race, men, right? And then when a woman comes in, and if it's typically for women and minority communities, the bank loan or house loan is denied, and that's how we are training, right? The model, then later on for testing, when a woman comes, right, the bank loan will be denied. And this is really bias, right? So we need to be fair. And the biases happen because that's really what has happened in the real world. So trustworthy machine learning, they have to be fair, they have to have high integrity, and they also need to make sure that that they are, okay, fair, integrity, data is accurate, data quality. So that's what trustworthy machine learning. So I just finished a sort of very high level paper on that. Okay, so now we go to the second part of the presentation. I've already talked, I think, for about half an hour, and I think I have 1 hour. So it'll take about another 20 minutes for me to finish this. Okay, so security and privacy for Internet of Transportation and critical infrastructure. So what is this Internet of Things? That's what one type of Internet of Things is transportation. So Internet of Things is really our clocks, anything that has a microprocessor. Clocks are talking to our smartphones, talking to our television, talking to our refrigerator, to our coffee maker or tea maker, to our Amazon purchases, let's see, to our smartphones and wireless, whatever, right? Everything's talking to each other. Sensor data, all communicating so that to keep us safe and to give us the best living experience. Of course, if these sensor data and these devices are attacked, it's going to be devastating. So what do we have here? Similarly, Internet of Things, there's Internet of medical things, Internet of financial things, and we have Internet of transportation. The cars are talking to each other, cars are talking to trains, to trucks, and to roadworks so that they all keep each other informed, right? Don't meet with accidents. What's the best route to take? What's the best restaurant that you can go to? Things like that. But imagine if these things are attacked, the communication, you could have chaos. So many accidents could happen, right? Okay, so Internet of Transportation, IoT has major implications in transportation. Autonomous vehicles, right? They aim at improving day-to-day activities such as delivering packages, improving traffic, transportation of goods. In US alone, trucks alone carry an estimated 63.3% of freight of goods, right? Autonomous vehicles, currently most of them have people, but a lot of things are automated, but there are also people-less, right, without driverless vehicles. AVs are not limited to ground vehicles, but also could aerial. Aerial could be airplanes and drones, and sea vehicles like ships and submarines and boats with a wide range of application. Levels of automation could be from 0 to 5. And it's interesting, right? We found that ground vehicles like cars, automation is 2, but aerial vehicles like planes, the automation is 4. Companies are investing heavily. GM spent, $728 million in R&D in 2018, it increased to $1 billion in 2019. I didn't get their numbers for 2020, and we also need to get the numbers for 2021. While there's great potential in AVs and the improvements it can do to the transportation industry, what's the biggest problem? Security, privacy. But a lot of the focus has been so far on security. Okay, security of autonomous vehicles. They are somewhat different from like financial data and network security data, right? AVs evaluate their environments using a variety of sensors, camera, GPS, inertial measurement units like IMU, LIDAR, radar, ultrasonic sensors. Previous research has shown that sensors are susceptible to malicious tampering, like IMUs are susceptible to sound waves and GPS receptors are susceptible to spoofing signals. And vehicles should verify the veracity of sensor signals before acting upon them, right? The veracity, the accuracy. So sensor-based, AVs rely on sensors to evaluate and interact with their environment, right? These are sensor-based. Inherited issues, sensors are susceptible to GPS spoofing and transduction attacks and manipulate the environment, physical signals like visual, sound, and magnetic. And then needed defenses, right? Classical computing security like memory protection, cryptography, and authentication does not protect against these types of attacks, right? Because they don't have space in there. There's not a lot of memory in those sensor devices. So we need some novel techniques and no verification because of real-time constraints. AVs trust and act upon their sensor data without any form of verification. So that's also a big challenge. So what did we do? So we came up with a physics-based anomaly detector. What do we mean by physics? Building a model of this physical system and then looking at the attacks. So we build a reference monitor. Reference monitor is that part of the system that has to be tamper-proof, because if your reference monitor is attacked, then the whole system goes away, it collapses. So we built a reference monitor, physics-based anomaly detection for ground and aerial vehicles. The algorithm will consist of 3 parts: building a model offline of the AV's physical invariants, implementing an online tool to monitor expected and observed behavior to detect anomalies, right? So we build an online tool to raise an alarm if significant residual difference exists between executions. So offline pre-processing, online verification, anomaly detection. Now you can ask, what's the big deal? This is something that we've been doing for 25 years or even more. Okay, the challenge here is the physics-based anomaly detection, the building the model, and then coming up with techniques to see how this model is attacked. Okay, so what is this? This is the physical model. So control systems folks like my colleague, Dr. Alvaro Cardenas, is a cybersecurity expert, but also an expert on control systems, right? So building this model like K state, YK input sensor measurements, preprocessor sensor and reading, UK commands to rotors, predicted states, LX, LY, and LZ or LZ, moments of inertia needed for nonlinear equations. M is mass, D is drag factor, and B is thrust factor. So this is what the model that we developed, built. And offline preprocessor, the autonomous vehicles invariants are calculated using well-known nonlinear models for aerial and ground. So we did for aerial and ground vehicles, right? So this is well known, but we have to build this model accurately. Accelerometer, gyroscope, and magnetometer sensor data on the X, Y, and Z axis, Z or Z axis is used for the aerial vehicle. Vehicle positioning and steering angle is used for the ground vehicle. Okay, so our online stage, we have an extended Kalman filter, EKF, is used to predict AV's physical behavior by estimating unknown parameters from noisy sensor input. Okay, the algorithm is divided into two sections that predicts and corrects the estimation before it's compared against the sensor data. So you can say Kalman filters have been around. Electrical engineers, control system engineers have been using it, right? And so it has been around. And so we are using a version of Kalman filters in this experiment, in this algorithm. And the anomaly detection, ACUSUM, CUSUM, is a statistical algorithm, is then used to detect persistent attacks. An alarm is raised if the residual difference is larger than a predefined threshold. Now, again, the question is, what's the big deal? Again, you've got to capture this model and then apply this Kalman filter, right? They're not applying machine learning, but that's the direction that we are moving, and I'll talk to you about it. Okay. So the physical implementation, you can see all the drones and the cars. We didn't do anything for the sea, not ships and boats. So aerial vehicle, we use Intel Ready to Fly Zone Controller, PX4 flight controller, focused on detecting. Remember, for AVs, we said GPS spoofing and gyroscope attacks. GPS attacks are detected after 0.2 seconds, while gyroscope attacks after 1.5 seconds. And the overhead we found was about 5.4%. Okay, by incorporating our security features. Ground AV, we built, custom built on top of Traxxas Ford Fiesta. Controller was ROS, Kinetic Kim, focused on detecting visual attacks on the camera. Attacks detected after 0.1 seconds, and overhead was about 2.25. Each threshold produces a probability of false alarms of about approximately 2%, right? So 2%, you can say, okay, it's very small, but again, today's standards, 2% is fairly high, right? If you have a false alarm of 2%, that's not good. We really need to bring it down to 0.000%, right? So 2% would have been great, say 15 years ago. I gave a talk about cybersecurity, data mining for cybersecurity attacks. And I said we had an accuracy of about what? We had false alarms, false positives, false negatives of around 25%. That time it was bad. They said it should be about 5%. But today, even 2 or 5% is not good. We need to make it to 0.00005%. Okay, so that's the physical implementation. Now, privacy, we haven't done a whole lot, but I'll mention in the directions. That's my third part. Beyond the security of individual vehicles, the transportation sector could greatly benefit from a supporting infrastructure that allows communication between vehicles, motion sensors of lampposts, and surveillance cameras to help identify traffic jams, reroute the vehicles, and increase vehicle safety. Right? It'd be really great to have privacy. Okay, without a doubt, what we're saying is we have to provide, apply machine learning and so on techniques to help the drivers, right? Identify traffic jams, reroute the vehicles, and so on. But from the user's perspective, there are privacy concerns because I don't want people to see me say smoking. I don't smoke, by the way, for people to see me smoking in my car. And I don't want people to know where I am at a particular time, right? So, because imagine if I'm smoking and somebody can take a photograph and send it to my insurance company, my privacy will be violated. From a user's perspective, privacy concerns arise from all information because a lot of information we need to provide safe and secure environment for the transportation systems, for the AVs. But By collecting all this data, just like earlier what I said for the healthcare, users' privacy is violated. So, and I'll talk to you later about the direction we are moving in. Legislators, engineers, and scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. And this will aid at improve the public perception, reduce hesitation from consumers, and increase the adoption rate of new technologies. Okay, so the third part is applying security AI for Internet of Transportation and Infrastructure. So applying part 1 to part 2. What are we doing here? So first is data science AI for transportation security. As I said, Internet of Transportation subject to attack. Like any cyber physical system, streaming data is being collected from such systems, including autonomous and in the future, driverless vehicles. As transportation systems go electric, we need energy conservation. Threats to the security of such systems could cause massive damage, including accidents, loss of lives, and so on. So the question is, remember I talked about data science for cybersecurity? Similarly, can we come up with data science machine learning techniques? Can we apply to analyze the data? So can we apply stream analytics for the sensor data for transportation systems? That's the question. So we have to understand the nature of the complex transportation data and adapt the stream analytics techniques and apply them to the sensor data. Okay, so that's what we are focusing on now. Second, I talked about adversarial machine learning, right? So Internet of Transportation will depend heavily on AI and machine learning, without a doubt, right? To find the best routes and communicate with each other, to help each other, to prevent accidents and so on. Data is collected, analyzed, so that's great. But adversary can learn about what our behavior, what our models in the car, and adversary can thwart us, right? And cause lots of problems like accidents. Therefore, the learning algorithms, whatever we learn, right, in order to provide a safe and secure environment, whatever we learn, right, we have to adapt it and thwart the adversary's actions. Eventually, it becomes game playing between us and the adversary. So what sort of games? Zero-sum, Bayesian, Stackelberg, and research on this topic is just beginning for Internet of Things and Internet of Transportation systems. With respect to privacy, look, earlier I talked about our smartphone. We built a policy-aware or privacy-aware, policy-based data management framework. Can we develop, we haven't done this yet, by the way, can we develop a similar framework for Internet of Transportation? So we have radar, GPS cameras, LIDAR, ultrasonic sensors going into this little gadget inside the car, and some data in the cloud, and we go through cloud-based services. And this is a privacy-aware, policy-based autonomous vehicles. So every step of the way, data collection, data storage access, data analytics, data sharing, this car talking to other cars and so on, has to be policy-based. Policies have to specify what sort of data is collected, how long will the data be kept, how do you store the data, how do you access the data, policies for data analytics and sharing. Okay, so this is, I would say this is the future for privacy-aware, policy-based framework for Internet of Transportation. My last chart, okay, we talked a lot of things, right? Developments in integrating cybersecurity and AI, exploding. We talked about AI for security, insider threat, security for AI, adversarial machine learning, also developments in privacy-aware healthcare and managing one's life's activities, privacy-aware quantified self. At the same time, with the development of Internet of Things, including Internet of Transportation and infrastructures, security and privacy solutions are being developed, mainly physics-based solutions. But driverless cars are becoming a reality. More and more AVs will use AI ML techniques, right? But these AI ML techniques could be attacked. So the question is, how can we develop AI solutions for detecting malware in AV systems? And how can adversarial ML work in AV systems? How can we develop a privacy-aware, policy-based data framework for Internet of Transportation? And again, how can we develop trustworthy machine learning analytics efficiently when so much of data is coming from all directions? What about formal methods for IoT security, right? So these are all opportunities for research. So numerous opportunities for substantial research and development. What I discussed, I think we could have 10 PhD theses. So lots of problems for all of us to work together. And finally, acknowledgements and thanks. Myself, of course, I mean, my name's there, and Alvaro Cardenas, Murad Kantajalu, Latifa Khan, Raul Quinones, and Rhonda Walls. Okay, so this finishes my presentation, and I'm now going to stop sharing. And as I said, this is a placeholder recording. And I will be giving this keynote address. It's what now? It's about 8:30 exactly, I would say 2 hours from now. Okay, in about an hour from now, the conference will open, and that's at 9 o'clock India time. And my talk will be 9:30 in the morning, February 24th India time, which is going to be 10 a.m. So the conference starts at 9:30 p.m. US Dallas time, Central Standard Time, and it will be 10 p.m. US Dallas time, that is Central Standard Time, when I will be giving my keynote address. Anyway, thank you very much for listening to this presentation. And again, as I said, it's a placeholder presentation just in case there's a technology glitch, and I'm going to send a link to the conference organizers, and hopefully everything will go well, in how many hours I said, hopefully everything will go well in 2 hours when I give the live presentation. Again, thank you very much.